A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear students, today our theorem is if f of x is bounded and measurable on AB close interval, then it is Lebesgue integrable on AB close interval. It means that if function f x is bounded and measurable, then the given function is Lebesgue integrable. Proof: given that f x is bounded and measurable on AB close interval, then we are to prove that it is Lebesgue integrable on AB close interval. Since we know that the upper sum capital S is equal to summation k is equal to 1 up to n ykm of ek, and the lower sum small s is equal to summation k is equal to 1 up to n yk minus 1 m of ek. Now taking over the subtraction capital S minus small s, summation k is equal to 1 up to n yk m of ek minus summation k is equal to 1 up to n yfk minus 1 m of ek. Now summation k is equal to 1 up to n is common, m of ek is common, yfk minus yk minus 1 is left. Since fx is given to be bounded, so for any pre-assigned epsilon greater than 0, we can find a partition yk minus 1 is less than epsilon divided by b minus a. Because the given function is bounded, so we can take this. The function is bounded, then yk minus 1 must be less than epsilon by b minus a. Now since capital S minus small s is equal to summation k is equal to 1 up to n yk minus yk minus 1 m of ek. Now summation k is equal to 1 up to n is as it is, m of ek is as it is, and instead of yk minus 1 yk minus 1 we will put epsilon divided by b minus a. Now epsilon divided by b minus a is common because summation does not apply on this. Now summation k is equal to 1 up to n m of ek. M of ek is the domain, and taking over the sum of all the n interval, this will gives us the length of the interval, which is equal to b minus a, or we can say that second minus first. B is the last point of the interval and a is the starting point of the interval, and the length of the interval will give us b minus a, second minus first. So b minus a will cancel with b minus a. This implies that capital S minus small s is less than epsilon. We call this equation 1 star. Now since we know that which states that a result if function of x is Lebesgue integrable on AB close interval if and only if for every epsilon greater than 0 we can find a partition such that capital S minus small s is less than epsilon. For a particular partition, if we find capital S minus small s is less than epsilon, it means that the given function is Lebesgue integrable because there is an if and only if condition. So from the start we have proved that capital S minus small s is less than epsilon. So according to this result, the star implies that fx is Lebesgue integrable, which is the required proof. It means that the function is bounded and measurable, then it is also Lebesgue integrable. Now we have next theorem. If we have two functions and fx is less than or equal to gx on e, then integration on e fx dx is less than or equal to integration on e gx dx. Proof: since fx is less than or equal to gx on e, so shifting towards left side gx, fx minus gx is less than or equal to 0 on e. We can also write fx plus minus 1 gx less than or equal to 0 on e. Now taking over the integration on e is the domain, fx plus minus 1 gx bracket dx is less than or equal to 0. We can distribute the integration on e fx dx plus integration of e minus 1 gx dx is less than or equal to 0. Now integration on e fx dx plus minus 1 is constant, so minus 1 we can take out from the integration, plus minus 1 integration on e gx dx is less than or equal to 0. Integration on e fx dx plus into minus minus integration on e gx dx is less than or equal to 0. Now shifting the negative integration gx dx towards the right side, so it will become integration on e fx dx is less than or equal to integration e gx dx.